That's great. Our data can now be reused throughout all of the states. Before we start adding the remaining states though, we'll take a look at how are we going to allow our player to move up and down slopes and also climb steps up until a certain height. For the reason why, let's enter play mode and move up and down in our small ramp. Even though for the most part it works, when going down or going up our ramps, we sometimes jump. If we head to the other ramp, we can't climb it either as there is a small step. The first one happens because Unity gravity isn't fast enough to keep with our horizontal movement speed, so it will look like we have jumped. The second one happens because we are colliding our player Capsule Collider with the ramp collider, which in this case is like colliding with a wall. It would work if the step was a bit smaller as it would hit the rounded part of the Capsule Collider, but it will be best for us to decide the maximum height we want our player to climb instead. From what I found when doing this system, there are two common ways of solving the slope problem: floating capsules and normals. Floating capsules, which is the solution we'll be using, consists in adding a force to the player in a way that the capsule constantly floats, or more specifically, the center of the capsule stays at a certain distance from the ground. We can mix this with the resizable capsule collider to allow our player to climb steps up until a certain height. Normals, however, involve getting the normal of the ground as underneath the player and set our player direction relative to that normal. Normal is simply the direction that the object is facing. However, I don't think normals solve the step climb problem, so we'll go with the floating capsule technique. With that in mind, we now have two things to do. Allow our Capsule Collider height to be changed through a slider, removing the height from the bottom only, and apply a force to our player to keep him from falling due to gravity. Let's start with the collider height. To do that, go to the scripts folder and create a new folder named Utilities. Inside, create another folder named Colliders. In here, we'll create a new C# script to which I'll name Capsule Collider Utility. Open it up and remove the default methods and inheritance. Because we'll need it to show in the inspector, we'll make this class serializable. In this script, we'll basically be recalculating our collider height every time a slider that goes from 0 to 1 is updated in the inspector. 0 being 0% and 1 being 100% of the original collider height. To do that, we'll need a few things: a reference to our capsule collider, the default collider data, and the slope data, like our percentage slider. We'll be creating a data class for each of these, including our capsule collider reference, as we'll need to cache some data from it as well. So, back into Unity, go to the scripts folder and create a new folder named Data. Inside, create yet another folder named Colliders. In here, we'll create 3 new C# scripts: Capsule Collider Data, Default Collider Data, and Slope Data. Start by opening up the Capsule Collider Data script. Remove the default methods and inheritance. We'll be storing not only our Capsule Collider reference, but also its local space center. So type in public Capsule Collider, Collider, and make it a private set. And then public vector3 Collider Center in local space, with a private set as well. To initialize this data, we'll create a new method by typing in public void initialize and pass in GameObject as a parameter. This is because we won't be setting our reference through the inspector, but instead through a GameObject we pass in. If you do want to set it from the inspector instead, then the next 3 lines won't be required, but you'll need to add the serialized field attribute to the collider variable, as well as the serializable attribute to the class. Making it a GameObject instead of a player makes this script reusable. Inside, type in if collider is different than null, we return, as it means it's already initialized. Otherwise, we'll get it by typing in collider equals to GameObject.getComponent of type Capsule Collider. For our Capsule Center in local space, we have 2 ways of doing it. One is by using the transform inverse transform point method to transform a world space position to a local space position. However, the Capsule Collider already contains a center variable in local space. We'll be setting it to our own property though, as that makes it so that if we ever need to update this center to be something else, we only need to change it here and it applies everywhere. Or if we ever need to remove it, errors will be thrown wherever we were using the property, which makes it easier for us to know where we need to remove it from. So type in ColliderCenter in local space equals to collider.center. We'll extract this last line to a new method named updateColliderData and make it public. That's it for our Capsule Collider data for now, so open up the default Collider data script. We'll need this data when recalculating the Capsule Collider new dimensions. Remove the default methods together with the monobehavior inheritance. We'll be making this class serializable to be able to set the default data through the inspector. We'll be needing 3 things: its height, its center, and its radius. So type in field, serialized field, public float named height with a private set. Then duplicate this line twice and swap the names to be center y and radius. I'll give the height a default value of 1.8f, the center y a default value of 0.9f, and the radius a value of 0.2f. The height of our character model is known through its mesh renderer bounds size variable. The center y is simply half of that height, and our radius is something we've defined ourselves before. That's it for our default data, so next, open up the slope data script. Remove the default methods and the inheritance and make the class serializable. We'll only need one variable for now, which is our step height. So type in field, serialized field, field range from 0f to 1f, public float step height percentage, with a private set. I'll default it to 0.25f. We'll add the rest of our variables whenever we need them. That's it for now, so go back to the Capsule Collider utility script. We'll create a variable for each of our data classes. To do that, start by typing in public Capsule Collider Data, Capsule Collider Data with a private set. Again, if you are setting this one through the inspector, add the field serialized field attribute to it. Then duplicate this line and swap Capsule Collider with default collider. When that's done, add the field serialized field attribute to this property. Duplicate this new line and swap the default collider with slope instead. We now have our data variables, so we can start creating the methods needed to recalculate our collider dimensions. To do that, create a new public method named Calculate Capsule Collider Dimensions. We'll be calling this method every time our inspector values are updated, so we'll need to recalculate the height, center, and radius. We'll start with our radius by typing in SetColliderRadius and pass in default collider data.radius. Then I'll make the method public just in case we ever want to reuse it. Inside, type in Capsule Collider data.collider.radius equals to radius. This is needed because we'll need to update the radius to something else later on under a certain condition. Once that's done, we'll need to set our collider height depending on our step height percentage. So duplicate this method and swap the radius with height instead. Then in our calculate method, call in SetColliderHeight and pass in default collider data.height. Of course, we need to multiply this with our step height percentage, which goes from 0 to 1, where 1 is 100%. So multiply the height by, between parentheses, 1f minus slope data dot step height percentage. We add the 1f minus here because the step height percentage is the percentage we want to remove. So removing 0.25 or 25% means that our new height should be 75% of its default height, which we can get by multiplying the default height with 0.75. With that done, we now need to recalculate our center. While our center is half of our height when the height is at 100%, this isn't true when we start lowering the height. The reason why is because we'll only remove height from the bottom to represent the step height, which means we want the capsule collider to center itself at the top and not in the middle of the character. Thankfully, it's quite easy to do that. We simply need to get the difference between the default height and the current height, and then add half of that difference to the center. Half here is the same as the bottom or the top part, and this basically makes it so that our top difference will add itself to the bottom instead. So call in a new method named Recalculate Capsule Collider Center. I'll make this method public as well. Inside, type in float collider height difference equals to default collider data dot height minus capsule collider data dot collider dot height. We get the default height first because our current height will never be bigger than our default height. When that's done, create a new vector tree named new collider center and set it to be equal to new vector tree 0f default collider data dot center y plus between parentheses collider height difference divided by 2f, and for the z axis pass in 0f. Again, we are making it go up off of our height, which is the same as adding our top height difference to the bottom. Then we set the center by typing in capsule collider data dot collider dot center equals to new collider center. Note that this collider dot center is measured in local space, so we can assign our new center without transforming it into world space, which, if you ever need, you can do it by using the transform point method. That's mostly it when recalculating the dimensions of our capsule collider, but we currently have a problem. Whenever we update our step height, it will come to a certain point where our capsule collider becomes a sphere from how small it is, and will start moving up when we keep removing height from it. It seems to happen whenever our height is less than double of our radius. is really simply because a capsule collider top and bottom are half spherical, which makes it become a sphere when there is no more middle ground to remove. So it starts going up instead, likely because it starts becoming a negative-like middle ground. What we'll do to fix it is simply set our radius to half of our height whenever the height gets to that point we've mentioned earlier. This makes it so that instead of going up, it will keep being where it was, but will instead become smaller. It isn't a perfect solution, but in my opinion it's better. So, to do that, type in if CapsuleColliderData.Collider.Height divided by 2f is lesser than CapsuleColliderData.Collider.Radius. If this is confusing, we basically need to know if our height is double or less of our radius. So if we divide our height by 2, we get half of it. If half of our height is equal to the radius, then it means that the full height is double of the radius. If half of our height is less than the radius, then it means that the full height is less than double of the radius. In the last case, we need to update the radius to that half height, which keeps our height at least double of our radius at any given time. To do that, type in SetColliderRadius and pass in CapsuleColliderData.Collider.Height divided by 2f. I'll also extract this half height into its own variable named halfColliderHeight and swap it in the method call as well. That fixes our problem, but we also can't forget that when we recalculate our center, we also need to cache our center in local space again. So call in CapsuleColliderData.UpdateColliderData. With that done, we now only need an initialization method, so above type in public void initialize and accept a GameObject named GameObject. Then call in CapsuleColliderData.Initialize and pass in GameObject. Of course, in case this class isn't serializable, which in my case isn't, we'll also need to instantiate it. So above, type in CapsuleColliderData equals to new CapsuleColliderData. And above that, type in if CapsuleColliderData is different from null, we return, as to not keep calling this once it's already initialized. That's it for our Collider utility, so let's now add it to our player. To do that, open up the player script. In here, create a new field serialized field public property of type CapsuleColliderUtility named ColliderUtility with a private set. I'll give it a field header with the text of collisions. When that's done, in the awake method, call in ColliderUtility.Initialize and pass in GameObject. Then, to make sure our Collider dimensions are updated, call in ColliderUtility.Calculate Capsule Collider Dimensions. This takes care of setting our Collider data whenever we enter play mode, but doesn't take care of setting it in the editor whenever we update a slider value. To do that, we'll call in the MonoBehaviorOnValidate method. We'll copy the two lines we just added in the awake method and paste them here. Saving and going back to Unity, every value update we do in the inspector should now recalculate our capsule data. Our Capsule Collider height is indeed updating fine. Of course, if we go ahead and enter play mode, our player will fall and have his legs be stuck in the ground, as our Capsule Collider is no longer the size of our character model. That's where the floating capsule technique comes to the rescue. Simply put, we'll add a force to counter the gravity pulling us down. The way we'll be doing that is somewhat simple. Let's take a look at our player model with its capsule. In the editor mode, we are able to update the Capsule Collider height by only taking away height from the bottom. Of course, because we are in the editor mode, there is no gravity and that's why it stays up. What we want is to keep this place even when we enter play mode. However, as we have seen just now, if we do enter play mode, our player will fall until it collides with the ground. This is simply because our character model is just plain graphics, and doesn't take care of any collisions, as we've left that for our Capsule Collider. The Capsule Collider then sees nothing underneath, so it will start falling down due to gravity until it collides with something. So how do we make it so that the player doesn't fall down due to gravity and stays at the distance it was in the beginning? We have our SetColliderCenter in local space, which currently, for our values, should be around 1.125. We'll then cast a ray down from the Capsule Collider World Space Center, as the RayCast requires a world space origin up until a certain distance. If this ray hits something, which shall be our ground, it will give us the distance between the origin and the ground hit point. We then shall simply remove that distance from our Capsule Collider local space center. There are three possible outcomes here: a positive value, a null value, and a negative value. A positive value happens when our Capsule Collider isn't yet where it should be and shall still go up. For example, let's say that in this position, the distance from our ray to the ground is 1. 1.125 minus 1 results in 0.125. This means that our player still needs to go up 0.125 units for it to be at our desired point, which can be done by adding a positive vertical force. A negative value is quite the opposite. It means that our Capsule Collider is above where it should be and should go down. For example, let's say that in this position, the distance from our ray to the ground is 1.5. 1.125 minus 1.5 results in negative 0.375. This means that our player went 0.375 units above its desired point, and needs to go down 0.375 units to be where it should be. This can be done by adding a negative vertical force. A null value happens when our Capsule Collider is at its desired point. For example, let's say that in this position, the distance from our ray to the ground is 1.125. 1.125 minus 1.125 results in a 0. This means that our player is at the desired point, as it's both up or down 0 units, which is perfect. Of course, we need to keep a few things in mind here. The first one is that we need to use our local space center for this subtraction. If we were to pass in the world space center, then the y could be 0, 1, 1000, minus 250, etc. depending on the player position at that time. The second thing is that we need to add a negative vertical force ourselves, because if we let Unity Gravity take care of it, it will be too slow and we will still have our slope jump problem. The third thing is that these values that we'll receive will be smaller than that 1.125 value, meaning that they will be extremely small. Adding a force with such a small number will not be strong enough to overpower Unity Gravity. Because of that, we'll need to multiply that value with a force multiplier to make sure it has enough force to go up or down as fast as it can, instantaneously to the human high if possible. Also, we need to remember that add force keeps on adding a force, so we need to make sure we remove the current vertical velocity, as otherwise our player will start bouncing. It doesn't end up flying because we'll also be adding a negative force for when we pass through the desired point, so it will keep coming back and start bouncing instead. The fourth and last thing is that it is very unlikely that our value will be null or 0. The reason why is because we are using physics. So by the time we call another add force, Unity's gravity will have added a tiny bit of negative velocity. But we'll still check if it is 0 so that we can return and do nothing if that's ever the case. We'll do all of this in our grounded state, so open up the player grounded state script. The reason why we'll do it here is because we really only want our capsule to float whenever we are on the ground, as the rest of the states, airborne and aquatic, won't really need it and would probably not work very well if we hadn't it there. With that in mind, start by overriding the physics update. I'll add this method to a new region named iStateMethods. Then call in a new method named float. You can name it float capsule or anything else if you prefer. I'll add this float method to a new region named main_methods. We'll start this off by casting our ray downwards towards the ground. To do that, we have the physics RayCast method. This method requires us to send the origin of the ray in world space, so create a new vector tree named CapsuleColliderCenter in world space and set it to be statemachine.player.colliderUtility.CapsuleColliderData.Collider.bounds.center, which returns the center in world space. Then we'll create a new variable of type ray named downwardsRay from Capsule Center and assign it to a new ray. For the first parameter, pass in CapsuleColliderCenter in world space, and for the second one, pass in vector3.down. As far as I understood, the difference between vector3.down and -transform.up is that vector3.down will always be in world space, while -transform.up will be relative to the transform rotation. When that's done, type in if physics.raycast. The first argument is our ray, so pass in downwardsRay from Capsule Center. For the second argument, we need a RayCast heat variable, which we can pass in out RayCast heat named heat, which allows us to use the heat variable inside of the if statement. This variable is what we'll use to know our distance. Of course, we now need a distance for the ray, so let's go to our slope data script, and when you are here, add in a new field, serialized field range from 0f to 5f, public float property named float ray distance. I'll give it a private set. I'll also default it to 2f. You don't really need it to be 2/2 here, but just a bit above half of the capsule height. Giving it a higher number ensures it works and will also be used for something we'll see later on. Back into the grounded state, we'll need the slope data, so let's go to our variables and type in private slope data. This is so we don't need to type in a long line as we'll use it more than once. Then, in our constructor, set the slope data to be equal to statemachine.player.colliderUtility.slopeData. Back to our float method, we can now pass in slopeData.floatRayDistance. For our fourth argument, we need the layer or layers that this ray will collide with. We'll only be colliding with our environment layer, but we don't yet have a way to get it. We could pass in its layer number or string, but that isn't a great way of doing it. We'll instead create a new script to hold this data, so head back to Unity. In here, open up the player data scripts folder and create a new folder named layers. Inside, create a new C# script named player layer data. Open it up and remove the default methods and inheritance. will make this class serializable. When that's done, create a new field, serialized field, public property of type LayerMask, named ground layer. I'll give it a private set. Then go to the player script and add a new property under our Collider utility by typing in field serialized field public player layer data. I'll give it a private set. Save and add back to Unity. Selecting the player object, go to the layer data area and set the ground layer to be environment. Back to our ground state, pass in state machine .player.layerData.groundLayer. For our fifth argument, we'll pass in query_trigger_interaction.ignore, which ignores objects that have the environment layer but are trigger colliders, as we don't want to consider triggers a ground we walk on. That's it for our if statement, so we can now start floating our capsule. To do that, create a new variable to hold our remaining distance by typing in float distance to floating point equals to statemachine.player.colliderutility.CapsuleColliderData.ColliderCenter in local space.y, as we want the vertical axis. Now, this isn't extremely important for us, but if we ever scale our player game object, our capsule won't stay afloat at the point that we want. To fix this, we can multiply this Collider Center Y with a player Y local scale. So multiply it by statemachine.player.transform.localscale.y. Of course, if the scale becomes too big, the distance will be more than 2, so the RayCast won't find anything, and our player will enter the ground, which is solvable by increasing the distance value. We now simply need to subtract the distance from our ray heat, so type in -heat.distance. This is, of course, the distance from the center of the capsule collider to the ground. We can now float if this value isn't 0, so first type in if distance to floating point equals 0f. We return. Then we'll need our lift force, which means we need a vector tree. Start by typing in float amount to lift equals to distance to floating point. We now need to multiply this value with that extra force we've talked about previously, and also remove the current vertical velocity. For the force, add back to the slope data script. In here, duplicate the ray distance variable and set the range to be from 0f to 50f, and name it step reach force. I'll default this value to 25f. When that's done, go back to the ground state script and multiply our distance with slope data.step reach force. We'll need to subtract it with the player vertical velocity now, so let's create a method to get a z. Go to the player movement state script and under the get player horizontal velocity, type in protected vector tree get player vertical velocity, and inside type in return new vector tree 0f state machine .player.rigidbody.velocity.y and 0f. You could also just return the y value if you'd prefer, which will return a float instead of a vector tree. Back into the ground state script, subtract the amount to lift with getPlayerVerticalVelocity.y. We now need to convert this float force into a vector tree force, so type in vector tree lift force equals to new vector tree 0f amount to lift 0f. Then to add this force, we call in stateMachine.player.rigidbody.addForce and pass in lift force and force mode of velocity change. Add force here is fine even though we have another add force when moving, because this one is a vertical force while the other one is an horizontal force. We will likely need to use the velocity variable if both add forces were for the same axis. If we now save everything and go back to Unity and enter play mode, our player should be floating, meaning that our capsule collider won't be touching the ground. We can also go up and down slopes without any jumps. Furthermore, it's now possible for our player to climb the other ramp step without a problem. Of course, we can see our feet entering the ground when going up the ramp, but Genshin Impact likely fixes this using IK or inverse kinematics, which we won't be covering. Regarding what I previously said about our float ray distance, which is 2f, this ray distance is also used when the player needs to go down. This means that if we jump or fall down something, let's say we fall off the ramp, if the distance from the center of the capsule collider to the ground is enough to be caught in the RayCast, we'll instantaneously teleport to our desired floating point, as we've added a negative force to move down. This, however, won't be too noticeable once we had falling in our gliding system. With that, we are now able to correctly move on slopes, so we'll add something else as well. If we take a look at Genshin Impact, the speed of the player is reduced when we enter a slope. This happens both when going up or down the slope. So back into our grounded state, in the RayCast if statement, we need to get the angle of the ground. That's easily obtainable by using the vector3.angle method, which returns the angle in degrees between two vectors. So type in float ground angle equals to vector3.angle. For our first vector, we'll pass in the ground facing direction, which we can get through the it.normal variable. For our second vector, we'll pass in our downwards ray from capsule center direction. However, this direction is going down, which is the opposite of the ground direction. So we'll instead do its opposite direction by adding a minus at the beginning. With this value, we can now set our speed modifier to something else depending on the given angle. So call in a new method named setSlopeSpeed modifier on angle, and pass in ground angle. I'll rename the parameter to be named angle instead. We'll now need to create a new property for our speed modifier when on slopes, as we want to make it be relative to the current state speed. To do that, go to the player state reusable data script, and when you are here, duplicate the movement speed modifier property and name it movement on slopes speed modifier. This will act as a percentage from 0 to 1. Back to our grounded state, we need to check if this angle is at a certain angle and only update our slope speed modifier when that's true. However, while adding an if statement is fine, we'll learn something a bit cooler: animation curves. This easily allows us to add different speeds for different angle ranges through the inspector. To get our animation curve, go ahead and open up the player grounded data script. In here, under our base speed, create a new field, serialized field, public property of type animation curve, named slope speed angles. I'll give it a private set. Save it up and go to Unity. Then, open up the second inspector tab to see our player's scriptable object. If we open up the animation curve, we can see an empty graph-like window, with a value from 0 to 1 on the left and 0 to 1 on the bottom. The bottom value is considered the time, while the left value is considered the value. We can read it as it having a certain value at a given time. What we'll do is convert this time into our angle and the value into our slope speed modifier. so it will end up having a certain slope speed modifier at a given angle. We could leave the time or angle to be from 0 to 1 for it to be normalized, but that will make it harder to understand angle ranges, so instead we'll change our time to be from 0 to 90. To do that, select the first curve preset at the bottom. Then right-click on the last key and choose Edit Key. In here, press Tab to go to the time field and set it to be 90 instead. Press Enter when you are done. Then press F to recenter the graph. This made it so that our time or angle will now go from 0 up to 90 degrees. Right now though, our slope speed modifier is always 1 at any given angle. Let's make it so that our slope speed modifier is 0.75 when the ground angle is within 15 and 55 degrees. To do that, right-click in the curve and press Add Key. Then right-click on the key and add it to be 0.75 on the value and 15 on the time. When that's done, press Enter and F to recenter the graph. Make sure the graph itself is selected or you will recenter on the selected key instead. Now add yet another key and edit it to be at 0.75 for the value and 55 for the time. Press F again to recenter. Right now our curve is looking like an actual curve, which makes it so that the slope speed modifier is actually descending from 1 to 0.75 as the angle increases instead of being either 1 or 0.75. This can be what you desire and is what makes animation curves quite powerful. But we want it to only be one of the two values. To do that is thankfully quite simple. We right-click on a key and open up the Both Tensions drop-down. We then set it to be constant. Do the same for the other key. Our values are now either 1 or 0.75 and not something in between. We do however have another problem. From our angle 55 upwards, it keeps being 0.75 instead of 1. To fix this, we'll edit the second key and set the value to be 1. The problem with this outcome though is that now our angle 55 is also 1. So edit again and make the time 55.1 instead. This now translates to the following. If the angle is on the range of 0 to 14.9, the speed modifier is 1. If the angle is on the range of 15 to 55, the speed modifier is 0.75. If the angle is on the range of 55.1 to 90, the speed modifier is 1. In Genshin, however, we can actually very slowly climb high-angled grounds up until a certain angle. After that angle will fall or slide instead. So swap the 55.1 key value to be 0.4 and then add another key for 65.1 and make its value be 0. Make the 90 degrees key have a value of 0 as well. That's done for our slope modifier, so feel free to close the animation curve window and add back to the ground state script. In here, we need a way to get the slope speed modifier at the given ground angle. That translates to get the value of the curve at the given time. Thankfully, we can easily do that by using the animation curve evaluate method. So type in float slope speed modifier equals to movement data dot slope speed angles dot evaluate and pass in angle. We now have our curve value or slope speed modifier. So we need to set it up by typing in state machine dot reusable data dot movement on slopes speed modifier equals to slope speed modifier. We are now setting our slope speed modifier using an animation curve. We'll also return this value, so type in return slope speed modifier and update the return type to be float. In our float method, get its returned value by assigning it to a new float variable named slopeSpeedModifier. Then, under that, we'll check if slopeSpeedModifier equals 0f, we return. This makes it so we don't float on grounds that have an angle that's too high, which makes it so that we can't walk on them and will fall or slide instead. Of course, we still need to multiply our movement speed with this new variable, so open up the player movement state script and go to the getMovementSpeed method. In here, simply add to the multiplication statemachine.reusabledata.movementOnSlopesSpeedModifier. When that's done, save everything and go back to Unity. Entering play mode and going to a slope should now update the speed that our player is moving at depending on the ground angle.